stepper motors will be controlling the robotic arm and the mast on top of the robots. The motors we use are easy to control. Forward and backward is very simple. We even have limit switch incorporation, so using the edge range of motion. So when you push it, it'll switch directions, but we could easily make that just stop it. The drivers also have micro-stepping abilities. Right now it's in full steps, but it can also do half steps, quarter steps, eighth steps, 16th steps, and even 30-second steps. We also are able to feed it a series of commands to rotate a certain number of degrees. Here it'll rotate halfway and then rotate back. And finally, we have a control for a smooth startup and slow down on the edges of the ranges of rotation. And finally, using the absolute control, we're able to keep track of how far it's moved from its original position. So even if you try to confuse it, it can reset with one push of the button.
These are our drive motors for Scorpio. So they're a hobby RC type motor. They're brushless outrunners. Actually, this is a brushless in-runner. It's driven by 3 coils from an electronic speed control unit, which is driven by our RC signal that we generate on this little board here. So it has 12 channels of RC signal, which is like a 50 hertz PWM-like signal. This Maestro board from Maestro Robotics helps us generate those and not have to worry about the timing on our beagle bone. The motor also has a Hall effect sensor inside, which has a sensor cable that runs back to the speed control unit. So the closed loop control lets us abstract away our target speeds and actually meeting those. All we're doing then is providing our target speeds with the RC signal. The motor is a very high revolution, or very high speed, so we have it attached to a 64-to-1 gearbox and then coupled to our output shaft. So we've put a piece of tape on there so you can see how fast this is capable of spinning. We're running this motor at 7.4 volts, which simulates what our battery, our lithium-ion cells will run. We're putting 2 3.7 volt cells in series. With no load, it draws around 2 amps of current. So the motor control is all performed by setting target speeds on the Maestro board. The Maestro board is giving us commands over serial via the C code running on the BeagleBone. We'll have four of these motors on board. They're each rated for 180 watts of mechanical power output. They're very powerful, and we're running with slightly large diameter wheels, so this thing could get going pretty fast, so that's why Bula is going to tell us about the emergency stop system.
In case of a buggy software, there will be circumstances that the robot we might not be able to control the robot and for it to do exactly what we want it to do. And in those cases, we'll have a e-stop solution here for safety reasons. So this is a hardware-only kill switch, basically. So we'll have this is e-stop disabled, but when we enable the e-stop, the robot will stop completely. The motors will just completely shut down, and that's done all hardware, no software involved. At least the software for the AI, none of that involved. And this is all done through the Zigbee radio inside the encasement here. It communicates with the Zigbee on the robot, and there's a local e-stop on the robot as well, which will trigger the motors to turn off, and that should stop the robot.
Hi, I'm Scott Butcher, I'm the co-captain of the mechanical team. This is our robot Scorpio. As you can see, it is not entirely complete, but we're very close to having it fully done, and I can show you a few of the interesting systems on the robot. So this is our pivoting joint system. It allows us to move up and horizontally for rock clawing motion, as well as up and down for small obstacles. All the components on this are designed and cut by the team, machined. So the stock has all been machined by a team. These are water jetted aluminum brackets and laser cut plastic brackets. We're still waiting on a few more CNC components before we can put the entire robot together, but we will definitely have those in the very near future. A couple of things that we will show you next are the claw design, which is designed to mount here, and we will show you that operating off the robot next.
Alright, so as you can see here, we have our jaw claw system. All parts have been 3D printed for the prototype stage. Two for generally linear actuators that control the claw. It has plenty of clamping force and tons of room inside, plenty of space for any size payload. And we will now do a demo to show the clamping force and the ability to lift heavy objects.
So here you see the three systems that are currently acting as surrogates for the robots, main server, and the client systems. These are all connected via the Linksys router on the side there, and this is to partially replicate the conditions at competition, where we will have a similar router but one that is 4G capable. Now, right now you are seeing the server system running, and you will notice that it is receiving a heartbeat pulse message, and the heartbeat pulse is right now what we use on the robot to indicate to the server that the system is online. Once it actually starts receiving the report heartbeat message, the server will know that there is a system ready to go, and then it will send a confirm control message back to the client. From there, the client can then send commands such as the set local vector message that you see being forwarded onto the robot. Next, we have the client here. Now this actually is sending messages before the robot has woken up, and you see that it is sending a request control message but is immediately receiving a reject control message. The server will continue sending reject control messages until such time as the robot has actually awoken and sent a report heartbeat message. And finally, at the end, you will see that the client receives a confirm control message, and immediately afterwards, it sets another test message, a set local vector message that indicates in what direction and how fast the robot should drive. This final bit here is the actual robot code. Here you will notice that it is sending repeatedly a repeat heartbeat message to the server. After a certain period of time, you will finally also see the set local vector message, and the printout shows the values that are being sent from the client, and that has been forwarded to the robot. And you will notice that they come out approximately correct, accounting for rounding errors of the conversion process in JAWS.